Welcome to another episode of The New Quantum Era. I'm your host, Sebastian Hassinger. My conversations with people working on the frontiers of quantum information science and technology are motivated by my curiosity and my deep interest in watching this scientific field evolve into usable technologies for computation, communication, and sensing. From the very first introduction to quantum computing that I had at a workshop at IBM's TJ Watson lab in 2017, I've been utterly hooked, but my fascination with emerging technologies didn't start there. In the early 90s, I founded an internet service provider while starting a master's program in communication studies at Simon Fraser University. By the mid-90s, I was leading a skunkworks project to build Apple's first customer support website, where we built our own search engine and editable web pages, and we're in the top 10 most visited websites in 1996. It was a lot of fun, and I made lifelong friends. Rest in peace to Mike Irwin. After the dot-com boom and bust, I shifted to mobile and then open source and big data and machine learning and so on and so forth. All along, I bounced between my own startup projects and internal innovation projects at large corporations like Apple, IBM, Oracle, and now Amazon. When you're bootstrapping a startup, it feels like you have to do everything with almost nothing, and you look at the resources of merging and new lines of business in large corporations with utter jealousy. However, all those resources inside a corporation don't come without a price. Without a doubt, some of the most challenging innovation goals to accomplish in my career have been those carried out inside corporations. Successful companies are proud of the things they've done that have led to their success and skeptical of any new thinking for fear it might disrupt the secret of their success. Even when an internal innovation is needed to deliver new areas for growth or to stave off new competitive threats, it can be very difficult to get the freedom of action needed to put all those amazing resources to work. Quantum technologies are still in their very, very early stages, with one foot firmly in the experimental physics labs and theory groups around the world. However, for quantum technologies to eventually mature and evolve into truly useful tools that can create new value for humanity, they will need to tap into corporate-level resources. Engineering techniques must mature, product feature sets need to be defined, operational models honed, and above all, the quantum industry needs to deliver. As exotic as quantum technologies are, they must be integrated into the tried and true tools of commercial success to realize their potential. Today's episode features an exciting conversation with a leader of a great example of corporate innovation. I spoke with Vijoy Pandey, GM and Senior Vice President of Outshift by Cisco. Outshift is the company's internal incubation engine, focusing on emerging technologies that target adjacent markets and personas. Their startup-like team's current initiatives span a number of AI and infrastructure topics, and most recently have included emerging quantum technologies. Vijoy explained to me how the Outshift model works, and then we dove deep into the potential applications in quantum communications that are of particular interest to Cisco. I was really surprised, actually, by how near-term Vijoy's use cases are. I was aware of currently deploying technologies like quantum key distribution and post-quantum cryptography, but you'll hear him talk about relatively near-term practical use cases like network time synchronization and even some applications in financial services like high-frequency trading. Even more exciting is Cisco's vision to build a scalable, interoperable platform for quantum technologies, which I believe will be crucial for progress in quantum across the board. By the end of my conversation, I felt like I understood Cisco's relevance to the quantum industry, and I was left with a real sense of excitement about what Vijoy and team will deliver. I hope you enjoy our conversation. Vijoy, thank you very much for joining me today. I love to start with just giving you a chance to tell sort of your story of how you've gotten to how your career has sort of taken you to the place you are right now. So can you give us a brief introduction?
Yeah, so if you really want to go back, Sebastian, I mean, I think I want to start from T0, where I got interested in computing in general. And surprisingly, it was in one of the spaces that people are pretty familiar with now, which is AI and chatbots.
Mm-hmm.
And this was back in at the cusp of 89, 90. So I was in high school. I'm dating myself here, but a friend of mine and I decided to build a chatbot. And this was on a BBC Micro, of all things,
Yep.
with 8 kilobytes or 64 kilobytes of RAM. And we decided to build it using export systems. And we tried to model it after Eliza, which was a
Right.
chatbot developed in the
Right.
60s. I said, yeah, maybe we can do one of those as a high schooler. But then we took it a step further and we said, let's make it in Hindi. And Hindi required a Unicode extension that had not been invented yet. So we went through all
Wow.
kinds of hoops to get Hindi going, but that's how I got into this stuff. And
That's fascinating. That's really interesting. Was there, I played with Eliza myself, and were there challenges in sort of adapting the architecture of the chatbot, the Eliza chatbot, to Hindi? Were there linguistic challenges other than the Unicode?
So it was export systems based. So there was a lot of hash tables and if then else's and things like that.
Right.
But it also led to some very incredible, interesting behavior because there were no guardrails.
Right.
And the chatbot was actually abusing back at us, which is, as a high schooler, that is incredible fun. And which is what got us into this, which is what got us into where I am today. So
that's
talking about
fascinating.
historical reasons, I mean, that got me interested in computing in general. But then I ended up doing distributed systems and software as my career. And that ended up with this role where I am right now, which is all about pushing boundaries and looking at distributed and scale.
Right. Right. Yeah. So, I mean, Outshift is a fascinating sort of model for incubating corporate innovation. Were you sort of in those internal incubation, internal innovation type roles prior to the formation of Outshift?
No, I wasn't. I mean, this is my first internal incubation role. I mean, I've been a CTO in the past, so there's a little bit of that, but CTO roles usually tend to be primarily architecture and vision,
Right.
or
Right.
they end up being all of engineering.
Yeah.
And this is a little bit different because we are structured like a bunch of startups
Right.
within a large behemoth like Cisco, and so
Yeah.
we actually we have capabilities all the way from engineering to product management to marketing to customer success and business development, just like a startup would, but at smaller scale. And we start ideating and then we start building products and looking at product market fit. We start looking at product company fit because whatever we build needs to be scalable by bigger Cisco. So product company fit is a big metric
Right.
for us. And as we walk on that journey, we start involving larger Cisco. So we start involving the product BUs, we start involving sales, biz dev, and so on and so forth from the larger
Right.
Cisco to then take it to scale. So it's a pretty interesting setup, and it's been working for 5+ years now, which
That's
is
great.
a testament to that setup as well. I've been at Google, I've seen various models, but I've been at Cisco for a while, and Cisco has had various models, but this has been working pretty well.
There's all kinds of risks that need to be managed in these type of internal incubation programs. As you said, I think one of the key ones is product company fit. Like you can invest time and effort in something that sort of doesn't have a future in the company that's actually investing. So that's great as a starting point. Were there other sort of things that you've encountered that you realized you needed to provide additional guardrails or additional sort of risk mitigation for the projects that you're fostering?
The way to think about this is, so we have a framework that we use to figure out which problems to go after. And one of the things that we first look at is, let's look at Cisco's core businesses, which is networking, security, observability, collaboration. Those are the 4 pillars. So look at problems that are adjacent to those pillars, both on a risk horizon as well as on a persona horizon. So, can we look at networking, but look at personas that are a little bit adjacent to who we talk to today?
Right.
So, that's a persona adjacency. And then we look at risk adjacency, which is, can we look at problems that are not in the platform side of the house, which is where Cisco products are, but problems that have technology risk or market risk? And two examples of those could be like technology risk is quantum. I
Right.
mean, we know that there is an up and coming and promising piece of tech, but it's not solved yet. I mean, there's a lot of hard problems to solve for,
Yeah.
and we don't know whether this thing will work out, right? So there's a little bit of that. So there's a little bit of technology risk, and then I would say on the market risk side, what we think is technology works, but it has not found a market yet. So we are
Right.
looking at use cases. We're looking at stability of the market is not evolving every 6 months. So I would put agentic AI in that space where
Right.
the tech works, but how big is the market? We all believe it's big, but beyond coding, software development, services, is there anything else that we've tackled? There are promises in science and drug discovery and so on, but we haven't solved it yet. So the market is
Yeah.
still evolving. We're trying to figure that out. So that's the risk angle to it. There's also risks around process. How do we move fast like a startup, but also
Yeah.
we are part of a large company? So we actually took a framework which said, let's take a look at how Cisco acquires and integrates startups, and let's flip that model
Mm.
to its head and really look at few things that we are paranoid about in terms of risk. So people and hiring, yes,
Right.
as a large company. Revenue recognition, yes, as a large company. I mean, those are things that you can't mess around with
Right.
as a publicly traded company. But everything else, yeah, you can bend the rules a little bit.
Right.
So we did that, and I think we have a pretty good rule book to follow at this point.
That's great, and it really draws on the history of Cisco as a very adept and high frequency acquirer of other companies. I was around during the .com. I'm dating myself. I'm around during the .com era, and I remember John Chambers being sort of the champion of growth through acquisition at that stage. That's very smart to draw on that sort of corporate cultural learning. You mentioned, quantum already. Let's jump into that, because one of the reasons I really wanted to talk to you is, as far as I know, like, there's something really compelling about quantum in the context of a corporate incubator of this nature, because there's so much uncertainty about the timelines, because there's so much uncertainty about the use cases. In some ways, it feels like, an old school, almost, Bell Labs style incubation model is what's needed, because there are sort of fundamental challenges to address. Do you sort of see this as more like foundational research or basic research, or is this still in the model of a startup, but with sort of more uncertain runways and timelines than the other projects you're working on?
So one of the hats that I wear, Sebastian, is also Cisco Research. So there's Outshift, which is the incubator,
Right.
and just sitting beside that is also Cisco Research, and also I've got Cisco Developer Relations, which is DevNet, because they somehow all of these three functions, and open source, by the way, as well.
Right.
So all of these things are sort of, they all need to come together in some of these incubation efforts that we're doing. Quantum actually started within Cisco Research and still sits primarily within Cisco Research. But
Right.
what we've realized over the past year is we are spending more and more of Outshift's resources, skills, and time on this problem, which basically is telling us that we are pivoting from the physics research part of it
Right.
to a systems operability
Right.
deployment part of the equation. And the one thing that I wanted to just point out right off the bat is, as Cisco, since we talked about the four core businesses or four pillars that Cisco has and the PCF, the product company fit, we are looking at quantum computing from the quantum networking and quantum
Of
security
course.
side
Yeah. Yeah.
of the angle. As you can imagine, And one of the surprises that we ran into, good surprises, over the past year or so, is that quantum networking is actually not that far out.
Right.
Whereas quantum computing is still being figured out, quantum networking is more like here and now than
Well, it's so
quantum
interesting
computing.
to me because you've really got a split horizon in a way, because post-quantum cryptography, quantum key distribution, those are existing technologies where there's more the more of the work is on product market fit and productization and finding the right way to deploy those technologies to solve customer problems. But actual entangled photons communicating, like flying qubits, sometimes people call them, that one's probably even further away in some sense at scale than quantum computing. Would you agree?
Well, I would say that flying qubits at scale is still some time away,
Right.
though there is a tremendous amount of pressure. Is one of those burgeoning sort of rising tide of innovations that are happening right now, where I believe that there is a transformer or a chat GPT moment in quantum about to happen. Because if you just look at the number of innovations in the quantum space over the last 2 years, compare
Yeah.
that to the last 2 decades or 3 decades, I mean, we are
Yeah.
seeing this exponential curve. And I think any moment now we're going to hit this point where we're like, man, this is it.
Right.
And it's suddenly now practical to use this piece of technology, and the tech risk has just gone down. But having said that, I mean, yes, flying qubits at scale, maybe a little bit further out, but flying qubits not at that much scale, but
Right.
in a way that can be leveraged for classical use cases is where I think the sweet spot is, which is what is giving us a lot of excitement. Where if you can do entanglement based quantum networking, but use that quantum network to solve for some classical use cases, like you pointed out a few. There are a whole bunch of security use cases.
Right.
There are a whole bunch of coordination and synchronization use cases that a quantum network, which is few qubits, is good enough
Right.
to solve for than building out this large hundreds of thousands of qubits quantum environment.
That's interesting. So when you say synchronization, coordination, do you mean literally like, keeping all the clocks on a network all in sync? That sort of synchronization?
That is a great use case. So one of the use cases that we came across is, let's say you're building these really large global databases.
Who would be doing that?
Who's doing that?
Everybody.
So my previous life, I was at Google. They had Spanner, and the way you synchronize clocks,
Right.
so Spanner is like catching your nose the other way around. I mean, there's so many infrastructure elements that go into just making sure that the clocks are synchronized.
Yeah.
That's a clock synchronization use case. The other use case that we just came across in the clock synchronization space is when we were talking to ESNet. This is the Energy Sciences Network. We were talking to Inder and team at Lawrence Berkeley. And they were describing this use case where you have all of these telescopes, radio or visual, scattered across the globe, taking pictures of space, the same little segment in space, the same little square, but from different angles on planet Earth, so that you can see movement. So you can sort of say, yeah, there is a meteorite coming our way. In fact, I can imagine there are many, many more things that they are searching for, which are human made, which are not meteorites, but let's not go there.
Right.
But to do that, you would need all of these clocks to be synchronized across the globe. And so how do you do that? So there are these large global synchronization problems. So that's clock synchronization. But beyond clocks, there is, in fact, one use case that has been talked about quite a bit, so I can talk about it. But decision coordination is a really, really big problem space. And so think about high frequency trading. And the way high frequency trading works today is there's a guarantee of fairness that an HFT provider gives to their customers.
Right.
And the way they can provide that fairness is by putting all of your customers in the same physical environment where The speed of light is not a problem.
Yeah.
Now, you and I know this, that how do you scale? Like, I mean, you fit all your customers in one location, especially in a location like New York,
Yeah.
where you have a premium when it comes to space. How do you expand and how do you grow that domain?
Interesting.
Well, you create a data center in New Jersey. But speed of light matters for algorithmic trading across New Jersey and New York. So how do you synchronize actions across New Jersey and New York, or for that matter, anywhere within the US or anywhere else, without incurring the speed of light tax?
Right.
And you do that by entanglement and teleportation. And so the number of qubits you need is not so many.
Right. I was going to say, it always feels like there's this challenge at this stage we're at, even as much progress is happening, as you said, with finding the use cases. That we've been so set on use cases that drive massive volumes of data at very high frequency. And this is almost the exact inverse, right? It's small numbers of data points with very high dimensionality. So it's like the interior space has to be very large to fit the quantum use case. But the actual number of bits that you're moving in and out of the device has to be really low. So it sounds like, that's an interesting one where that may be the case. Is that sort of, were you looking for those characteristics in particular and sort of hit on this use case?
So we're looking at it as a spectrum. So if you think about, if you talk to us and you ask us what's our vision for, what is Cisco's vision for quantum computing? And our answer is, we are in it for the distributed quantum computing game. Right. We are a distributed computing company because through our network, you can take many similar or dissimilar computing devices, connect them, put a layer of software above it, and enable scale-out distributed computing. And we've done that with classical computing. And all the hyperscalers build out computing that way. Why should it be any different in the quantum space? And to do that, you need the quantum network. So the North Star vision is to build out the quantum network for the data center so you can scale out and you can get to hundreds of thousands or million qubits of usable qubits faster than any singular vendor would do. So that's the North Star. The other thing that allows us to do is you can put disparate technologies on the same fabric. So instead of betting on trapped ion or whatever, right? So all of the 8 or 9 technologies that exist there.
Seems like more of them every day, actually.
More of them every day.
Variations.
So don't bet on them, man. In fact, what you and I hear about is like each one of those technologies are probably good for certain things.
That's right.
So they will all coexist. And how do you make them coexist in the same fabric? By making them connect through a common fabric. And so that's our North Star vision. And then connecting more of those data centers, connecting sensors and building up the quantum. But that's the North Star vision. But what we realized is as we were building those pieces of technologies out, hardware, protocols, application, software, as we were building those out, those same protocols and software and hardware pieces can solve these classical problems today. The decision coordination, the clock synchronization, the eavesdropper proof security, the secure position verification. So a bunch of security problems, bunch of synchronization problems. And so what excites us is the here and now of using that stack or solving it in the classical domain today. And that's where we're seeing a lot of activity as well from the hyperscalers, from financials, from energy companies, who are all coming in as design partners.
You mentioned, positioning, and that brought the topic of sensing to mind. It feels like quantum sensing is again sort of ahead of where computing is because you can have these sophisticated but relatively simple devices as compared to hundreds of qubits working in a single system. But you still have the problem of getting that quantum data into your classical infrastructure so that you can process it, so you can use it in your application. Is that one of the categories you're sort of looking at? Is connecting quantum sensing applications?
Right. So to us, the roadmap on the quantum networking for quantum use cases side goes from building out this fabric, quantum network fabric, within a data center, which actually allows for heterogeneity and operability and distributed scale-out computing. Then connecting multiple of those quantum data centers, so almost like a data center to data center quantum network, and then connecting out to even quantum sensing that enables the quantum internet. So that's for the quantum computing side. And then in parallel, using that same stack for the here and now problems, which is, can I solve for these coordination, synchronization, and security use cases in the classical domain today, but leveraging the same quantum networking stack? So to us, that is the entire gamut of what we're going after. But the here and now in the classical use cases are actually the ones where we're seeing a lot of traction. Because people are coming to us trying to solve these high frequency trading problems, trying to solve these security problems and position verification problems. Because you're not sending quantum data per se, but you're leveraging the properties of entanglement and teleportation, or the collapse thereof in the security side to solve these problems. And so you can do it way more simply. You don't need these mega cryo chambers. You don't need these big detectors. The problem just simplifies dramatically, which is what makes it pragmatic today.
That's interesting. And you mentioned, people coming from HFT and, asking for help with these problems. That sort of begs the question about collaboration. I mean, you've got sort of, in these kinds of internal incubation efforts, you've got three potential sets of collaborators, right? There's sort of customers, there's startups, there's actual like pre-seed or seed stage startups and other external partners. And then there's the academic research world, which in quantum in particular, but also in AI and ML, because they're still very early stage technologies, there's a lot of activity going on in the research universities, in the national labs. Are there, sort of preferred modes of collaboration for Outshift?
It's all of the above. So we are part of, so Outshift is an internal incubator at Cisco, but we sit within the Chief Strategy Office. And the Chief Strategy Office, of course, has strategy for the company. It's got the corporate development arm, which is investments and acquisitions. And then it's got incubations, which is my group. And we work pretty closely together. So, for example, on quantum, we have investments in some companies and startups because, like we discussed, I mean, the physics is still not solved yet. There's some parts which are solved, there's some parts which are not solved. And so we need the partnerships, and we need 1,000 flowers to bloom because we don't know which one will go where. But we are building out on our vision on the hardware, we're building out on our vision of the software. Then we're also working with larger vendors on the computing side, you can imagine, because a network needs computing and computing needs networks. So there's a symbiotic relationship there. So we're working with some very large vendors, which I can't talk about right now, but there's some interesting announcements coming in that space.
Great.
And then we are working with these design partners because they're not customers yet. Like I said, we are on the quantum side, we're bridging between research and incubation for now. So everything that we've announced is research prototypes. We are very careful to say that because things are not available at scale yet. And so they are design partners, and most of the design partners, like we discussed, are high frequency trading or financials, or not just HFT, but other security use cases. They're federal agencies, they're energy companies where security, synchronization at scale, etc., matters to them. I mean, it doesn't matter to a person like me buying socks on Amazon. I mean, it's not going to matter to me. But there are not these yet. Really that's not the first use case, but but there are use cases where this matters today. So those are the kinds of design partners coming in.
Right. Right. And the academic world, do you collaborate with researchers at
Sorry, I
universities?
forgot to mention that. Yes,
Yeah.
there's a lot of
That's
academic.
my normal guest. That's the normal pool I draw from guests. That's why I'm asking about
No. So
the
there's a
researcher.
lot of work happening with academia. In
Yeah.
fact, the first announcement, almost like the coming out party that we had on quantum from Cisco, was this piece of silicon that we developed in collaboration with UC Santa Barbara. And this is a photon entanglement source chip. And what it does is actually generates 200 million entangled pairs a second
Wow.
in chip. Yes, when you deploy it, there are other reasons why you will get less than
Right.
that. But within the chip is going to generate 200 million entangled photon pairs a second. But it does that at room temperature, at telecom frequencies,
Right.
and at really low power. And these three things are important because you can throw thousands of these chips at a problem. Is low power, which implies low cost. It's at room temperature and it's at telecom frequencies, which you can deploy these in current environments without ripping and replacing your current fiber infrastructure.
That's incredible. Yeah.
Which is what allows us to do these classical use cases without specialized without specialized equipment in place.
Do you have? I mean, there's a number of sort of pilot quantum networks up and running in Illinois, in New York, in Europe, and a bunch of places in Asia. And Singapore has got a quantum safe network. Do you view those pilots as potential collaboration test beds, or do you have your own test network, or a combination of both?
It's a combination of both. So we are actually collaborating with quite a few of those. We've joined a bunch of consortiums in this space.
Right.
But the one thing that we are also realizing is that quite a few of them started out from, let's solve QKD.
Yeah.
Quantum key distribution. And we are of the viewpoint that, yes, security is a massive problem to tackle. But instead of going all the way to QKD, you can actually do quite a bit.
Right.
Before that in the technology sense. So a simple thing like, since our chip again sends entangled pairs at telecom frequencies, you can send those entangled pairs on a regular classical fiber alongside classical IP. So if somebody is actually eavesdropping and tapping into your network in any classical network, I can tell you provably that there's somebody in your network. And so you can leverage standard TLS, the NIST compliance, PQC, post-quantum cryptography standards, or QKD. I mean, you can go anywhere in that spectrum.
Right.
Even with standard TLS, I can tell you, man, there's a intruder in your network.
That's fascinating.
And so we are a little bit broader, and we are trying to meet people where they are. And that's why we have this strategy which says, this chip is going to give you quantum networking on the infrastructure that you have today. And we are also building out a software stack which says you can deploy the software stack alongside your current networking stack to turn on quantum networking capabilities alongside what you already have.
Boy, that's talk about future proofing.
We all know, Sebastian, that the world is not greenfield. So if anybody comes to us and says, let's start from scratch, that is not the answer anybody wants to hear.
Yeah. I always think how unique this the point of evolution of quantum computing and quantum technologies in general is, because in one sense we've reset the clock to the 1940s. And in the other sense, we have the cloud and open source and open standards and GPUs and massive amounts of compute and storage to help us, and also the pattern, right? I mean, the history doesn't repeat, but it does rhyme. It feels like we're able to draw on the lessons of the past, and this is actually where we can end on this question, because I've just been wondering about this as we've spoken from the beginning. You mentioned distributed quantum computing and the fact that there are these multiple modalities that likely are going to persist over time and have different roles in these distributed computing infrastructures. since your focus is on networking and communications and security, do you think it's possible that you'll expand into computing in the context of transduction, right? I mean, taking a microwave qubit or a trapped ion or an atom-based qubit and connecting it to another physical qubit somewhere is going to require photons. It's going to require flying qubits. It's going to require telecom bandwidth. So you have all the ingredients to be the glue in these distributed systems. Is that sort of in your long-range thinking, is getting into computing in that sense?
So the way we think about the quantum computing world, and you hit upon something which is the way we think about quantum computing is the supercomputer of the future is going to be, it'll comprise of CPUs and GPUs and DPUs, all kind of XPUs, accelerated PUs, on the classical side, as well as QPUs, or quantum processing units, on the quantum side. And a combination of all of these is what's going to drive the drug discovery of the future or the material discovery of the future and make your and my life much, much, much better to where we are today. So that is the viewpoint. But the way we like to phrase that problem is by saying quantum computing has a scaling problem and classical computing has a physics problem. And the quantum network is actually the solution to both of those problems. And so to us, the quantum network is actually the bridge between all of these problems that we're facing today in scaling out supercomputing of the future. But remember how we started? This whole thing is in the tech risk bucket.
Right.
And one of the biggest problems to solve to make this, the grand challenge here is transduction.
Right.
And transduction, and like I joke within the team, is it's always the goddamn NIC card. So if you really think about it, at a 10,000 foot level, is the NIC card. Is the thing that connects.
A really exotic one.
A really exotic one, but it is the NIC card.
Yeah.
So it's always the NIC card. I'm sorry, but it is the bridge between computing and the network, and it is a grand challenge.
It kind of put in those terms, it makes a lot of sense that Cisco would be right at the center of this grand challenge, doesn't it? So
That's right.
Thank you. That's really a fantastic framing from it. So any sort of last sort of perspective, any sort of the goals you have for the near future, or the types of things that you see in the next 12 to 18 months for the industry or for Outshift?
I believe that we are moving from a very physics-based approach to quantum to where we are heading into a systems-based approach for quantum, which means thinking about operability and interoperability and a brownfield environment, not just within quantum, but across quantum and classical. And we are at the cusp of solving those problems. And once those get solved, the transformer or the chat GPT like moment for quantum is about to happen. And it'll be one day and everybody is going to wake up and realize there is a step function that just happened. What do I do about it? And unlike other step functions in computing, where most of them have been software based and you could catch up, this one is going to hit you hard.
Yeah.
So you better prepare would be my message to everybody listening.
Really, really wise words. So thank you very much, Vijoy. This has been terrific. I really appreciate your time.
It was great fun. Thank you, Sebastian.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.